So a while back, I showed you how to do nonlinear regression in Python. On that occasion, we just did the fittings, but we didn't know anything about the fitting parameters. It is very important to know the significance of these parameters because to know if your procedure was significant or not, or in other words, if it's valid, if the model that you fit is valid, you need to know the significance of the parameters. Other programs like R and several other programming languages like MATLAB and other statistical packages like Origin or other graphing programs like Origin and other analogs, they can do nonlinear regression, and they will give you the significance of the parameters. But those are paid programs, or those are not free software. You can do the nonlinear regression in Python, which works very well, especially because it uses the Levenberg-Marquardt algorithm. So what I did today was to include code to show the significance of the parameters and put a pseudo R squared. So now when you run this program, you can have an idea of if your fitting is good, if your fitting is adequate by the procedure. So the procedure will let you know if there's convergence or not. This is from the procedure. But the code that I included here, we will show you the values of the parameters, the error of the parameters, the t-value, and the significance of the t-value. I also added in the pseudo R-squared, like I mentioned, and the sums of squared deviations. So I'm not going to write the code here because it took me a little bit to get this code together because I had to check a lot of the statistics in this. So we just maximized here a little bit. So this is the code. I'm gonna check it every important point here, and then I'm gonna run it to show you how it works. So this is just a comment, what the procedure does, who did it, and the date. This is the dependencies that you're gonna need to run this program. You're gonna need matplotlib for the plots. You're gonna need numpy for numerical manipulations and numerical calculations. You're going to need the curve fit from SciPy optimize to do the nonlinear regression using the Levenberg-Marquardt algorithm. You're going to need the pandas as PD here to import the data. And you're going to need SciPy stats, the T module here, to do the probability associated with the parameters, or the t-tests associated with the parameters. So this here, using pandas, imports the data set. The data set is saved here in my computer as a txt file. And an important note here, I got this data set, I got the idea from this data set from this site here. You should check it. So what they do here in this site is that they use this data set of volcanic eruptions and waiting time for the next volcanic eruptions, and they fit the nonlinear regression here using R. R already gives you the significance of the parameters and all of that, so I use this to compare, and then I also ran my program in R for comparison. But I feel that because of the Levenberg-Marquardt and because how Python works, I feel that it works a little better. But check this site here if you're more interested in the theory, because I can't go into all the theory. I'm just going to do something practical here. So this imports the data set. I'm going to put the data set on GitHub as well. It's an open data set, a free data set. Put here a print for if you want to check the data set, you just need to uncomment here. So all of this with the hash symbols here, hashtag symbol, or the number symbol here is a comment. If you want to uncomment, just delete here, comment, put the symbol here. So if you uncomment this here, the print, it will print the data set to the terminal. Okay. Another thing is that I'm on Linux here, but the procedure, the code should work equally as well on Windows. I have a video showing you how to install Python in Windows and how to run this in Windows. So it's the same thing. The difference here is that in those other videos, I showed you how to run Python in the idle in Windows, but here we're just going to compile it from the terminal, but it's the same thing. So, so this is to show the data set. This is the initial values of the parameters. What we're doing here, we're fitting a nonlinear model, sort of like a sigmoidal function to this data. So this S-type function here, and this is the model that we're fitting. So we're fitting this model here. The model is fx or y, waiting for the next eruption as a function of x. X is the duration of the eruption, and you have here 1, 2, 3 fitting parameters, A, gamma, and tau. So I define these parameters here in the model, and we're going to need initial values for those parameters, like I mentioned in all other videos that I dealt with nonlinear regression. I'm saving these initial parameters in a vector, and here I'm defining the function. So this little macro here defines that function, a over 1 plus exponential gamma minus gamma times x minus tau. So NP here is because we're using NumPy to invoke the exponential function. Okay, so the function is defined here. The initial value of the parameters are put in this vector here. And now we're using the curve fit procedure to fit the data using the Levin-Bergmark algorithm. I explained a lot of that on the previous videos. If you want to put a custom function here, if you want to fit your nonlinear function, you just have to change it here, change the parameters, and then every time you see the data set, ft eruptions, ft is the name of the data set that I imported. So eruption is a variable on this data set. It's the x variable. And ft weighting is the y variable that it was imported in this data set. Okay, so you just need to set your variables, and anytime you see this, you need to change the name to whatever name you gave to your variables. So this fits the curve. It needs the initial values of the parameters, and the method here, like I mentioned, is Levin-Bergmark. We have here popped. You can call this whatever you want, but in all tutorials, it's called popped. So let's keep it as popped. Popped is the value of the best fit parameters, and pcov is the value of the covariance matrix of the parameters. So this here is the part that I included. This is just going to print a little table in the output like you used to see in old school programs in Quick Basic and Fortran and all of that. So I decided not to put a visual window because that would be a lot of work for right now. I might do that later. So this here will print the covariance matrix like I'm indicating here. So I'm calling to print the pcov. This here will print the fitting parameters. I'm calling here popped. Popped is the values of the parameters. This here calculates the degrees of freedom for the statistics, for the calculation of the statistics. In those procedures, the degrees of freedom are defined as the n, the number of observations in the data set. So we have 272, if I'm not mistaken, or 73 observations, and D here is the number of parameters in your model. So the total number of observations minus the number of parameters gives you the degrees of freedom for the statistical procedure. The standard error of the estimates is the diagonal of the covariance of the covariance matrix. Okay, so not exactly the diagonal, but the square root of the diagonals of the covariance matrix. So this here, I'm extracting each of the, I have three parameters. So I have a 3 by 3 covariance matrix. I'm extracting the first component, the central component on the position 1, 1, and the component on the lower right corner on the position 2, 2. So I am extracting each one of them by defining the coordinates here on the matrix, on the data matrix, and I'm applying the square root transformation here. So this defines the standard error of the estimates. You can check on this site that I indicated to you. They talk about the theory about that, and this way that the parameters are defined, it's by linearization of related to this matrix, to this covariance matrix. There are several methods you can use. uh, Likelihood estimates, you can use several other types of estimates, but this is the simpler mathematically, so we can use it. We can do a simple implementation in code here in Python. The t-value is the value of the estimate given here by popt, or the best fit parameter. Here I'm extracting, see here that this is a vector of parameters. I'm extracting here the first for the t-value associated with it, divided by the square root of the first element of the covariance matrix. And the same thing for the t-value of the other uh, best fit or best estimate of each parameter. So this here is the parameter A. This here is the parameter, this here relates to parameter gamma, and this relates to parameter tau. Same thing here. This is the standard error for the parameter A, gamma, and tau. This here calculates the significance associated with the parameter. So the significance, you can check, again, you can check that the site that I showed you. There they use a function in R to calculate, to demonstrate how this is calculated. This is calculated automatically in R, but you can calculate it sort of manually as well. And the significance there is 1 minus, defined by 1 minus the cumulative distribution function for the t distribution, multiplied by 2. Here, instead of using 1 minus the CDF, we will use the SF, the survival function, which is equivalent to the 1 minus CDF, but it's more precise, like you can check here on the SciPy stats documentation. So this here gives the probability for the t-value for the first parameter A, for the gamma, and for tau. I did a little macro here, a little function here, just to see if there's the degree of significance. They're non-significant if they're greater than 0.05. They're significant here, 1 star from 0.05 to 0.01, 2 star significant at 0.01, if it's between 0.01 and 0.001, and else if it's less than or equal than 0.01, 3 stars here to indicate the significance. So this is often seen in statistics. It helps you just check visually and quickly if the parameters are significant. You see this in analysis of variance and several other procedures in statistics. This here is kind of messy, but this prints the matrix, not the matrix, but the table, the significance table of the parameters. So it's kind of messy here, but it prints well on a terminal. You could also make all of this automatic. I mean, you don't need to define those parameters. You could extract those parameters and do all those calculations on the covariance matrix. But I did it here on a more manual way because it's faster, and I was more worried about the statistics than anything else. So I'm going to try to decrease here the size so you can see what I have here. So I have here the text that's going to be printed, parameter, the estimate, the value of parameter, the standard error, the t-value, the probability, and this significance function here. Okay. So this here, I put some spaces here to try to organize it and align it. And if you put your own model, it might be not so aligned depending on the values, but you can change it here so it appears aligned. There's probably ways to put this table, to create this table in Python, but I didn't look at that. Like I said, I was more worried about the statistics than anything else. This is just to indicate a legend for those significance values. Put this here big again. This here will calculate a pseudo R squared. This R squared is not really defining nonlinear regression, but I'd like to look at it to have an idea. But the pseudo R squared here is the coefficient of correlation between the predicted and estimated values of the weighting times here. So the coefficient of correlation and the coefficient of determination is the R to the power of 2, or R squared, obviously. Okay. This here prints this pseudo R squared to the terminal and puts a warning note here. You need to be careful with the R squared when you're doing nonlinear regression. This here calculates the sum of squared deviations and the degrees of freedom. The degrees of freedom we calculated up there. The sum of squared deviations is the square root of the square differences between predicted over minus estimated divided by the number of the degrees of freedom here. So it gives you an idea of the precision of or accuracy. I don't remember exactly which one, but one of those of your model. Okay, so this is the end of the problem. This is just to be printed, and now we're going to do a plot as well. So the plot, you have the best fit line and you have the data. This is just simulated data, so you can have a better, more smooth predicted line. Okay. So let's go to another window here, and let's run this. Okay. To run this, I'm gonna invoke here Python 3 in Linux, and I call this here faithful because it's the name of the data set .py. And let's run this here. Here you have the plot. This is the best fit line in yellow. Here is the data. The data is very scattered everywhere. Found that the procedure works well. It worked a lot better than R. I did some tests in other models, and it worked. The conversions was a lot better than in R. Let's look at the output now. This is, like I mentioned, an old school type of output like you would see in old Fortran or C or basic programs. So this is the title, Nonlinear Regression Diagnostics. This is the covariance matrix. Like I mentioned, you have here the diagonal element 0, 0, element 2, 2, element 1, 1, and element 2, 2. And you get the square root of this to do the statistical calculations. This is the best fitting parameters. So A is 93.11, gamma is 0.64, and tau is 1.46. This here is the significance of the parameters, or the statistics on the parameters. A, this is the best estimate. This is the standard error of the estimates. So the plus or minus, this is the value that's plus or minus associated with this estimate. This is the t-value. It's simple this divided by this. And this is the probability associated with this from this survival from the t-distribution. Calculated from the t-distribution, usually the 1 minus the cumulative distribution function, or the survival function times 2. Each of those times 2. This is the significance, so the parameter is significant, 0.01. Same here, 0.63 for the gamma, 0.10, 6.25, also significant. Same here for tau. So the model is significant. You can use this model to do predictions. If one of those parameters were not significant, you need to evaluate if the parameter is needed, or maybe the data set is not that good, or the model is not good for the data set. Okay? This prints the pseudo R squared. It's around 0.02. R squared in nonlinear regression is usually high, so be careful with R squared in nonlinear regression. This is the sum squares of the residuals, 5.676, and the number of degrees of freedom, it's the number of observations minus the number of parameters, which is 3. Okay, so you have 2.72 observations. Okay, end of problem. Just to indicate here that the procedure is finished. I'm going to close this graph here. And you can adapt this to your model. Just be careful where you need to change. So you need to change the parameters, you need to change the model, and everywhere you see the parameters or the variables being used, you need to change for your own code.